Thanks, Marike. On behalf of myself, welcome everybody to the June webinar. Today I will be talking about the Sequence Stratigraphic Interpretation System, or SSIS, in OpendTect. So let's get started. First, here's an overview of today's webinar. I will give you a brief introduction, followed by some basic concepts. Lapout Patterns, what models we offer, applications, and so forth. Then we will have a look at the workflow briefly. Then I will present to you a little case study from the Penobscot dataset, offshore eastern Canada. Then we'll do a little recap and then conclusions before opening up for questions and answers. So let's get started. So SSIS started as a consortium back in 2004. That was the first phase of this consortium, where this tool was developed together with other geoscientists from companies that took part in this consortium. This is again an example of how we develop tools together with people in the industry as a collaborative effort. At the base of the Sequence Stratigraphic Interpretation System is the HorizonCube, which is the global interpretation method from DGB in OpendTect. So we'll also have a look at what a HorizonCube is and so forth, just briefly. The name Sequence Stratigraphic Interpretation System implies that it is for, of course, sequence stratigraphic interpretations, but in fact this tool has multiple applications, as we will see. The idea here is that with the HorizonCube we can pick phase-consistent horizons, a dense set of semi-automated horizons in the data, and with these slight subtle thickness changes and so forth, we can see shifts in the stacking patterns and shifts in the deposition of sediments that would be otherwise hard to detect just with the naked eye. And this is especially evident when we use the structural domain in combination with a flat-end or Wheeler type of scene in OpendTect, which we will have a look at in the demo. So that's just to give you a brief introduction to SSIS. So let's have a look at some concepts next. So I wanted to talk to you about some, my example here is kind of a textbook example of Lapout Patterns. These can be helpful when you start an SSIS type project. Then we'll have a look at the models that are available in SSIS, or what comes shipped with SSIS. Already here it's important to stress that this tool is flexible in a sense that you can create your own models if none of these models that we provide suit your needs. And then we'll have a look at some applications. But let's get started with Lapout Patterns. This sort of lies at the core of what we do here. So SCPM defines lateral termination of strata at the depositional pinch out or lapout can occur at the upper boundary of a sequence, where it's called a top lap, or at the lower boundary where it's called on lap or down lap. So what you're seeing here is down laps at the bottom here onto a down lap surface, and at the top what it looks like, what this is supposed to represent, is an unconformity. We have something called truncation. This red line, wiggly line here, is the unconformity, so it's been eroded. When the base level will start to rise, we will get these shapes here, which have on lap onto this previous surface and down lap onto the down lap surface. We further raise the base level and we may get a package like this, where we have again down laps and what we call top laps. Then when the base level starts falling again, we may get something we call a falling stage, where we have this type of pattern emerge. These are called off laps here at the top, and again a down lap onto this down lap surface. When the base level starts rising again, we will again see on laps onto this previous package. And this then builds our sequence. Now in my case here, the sequence boundary is here marked in red, so this would be one sequence. Then you sort of start over and the whole thing happens again in a textbook example. Now sometimes you may be working with just a small piece of seismic, small volume. You may not be able to see these big picture patterns. All you may see is just characters of your seismic reflectors, for example. So at its simplest, it might be just a layer cake parallel type of situation. We may have subparallel reflectors or divergent reflectors. In a more regional view, we may see more kind of normal or forced regression type of patterns. So in a normal regression, you get sort of a gradation and progradation like this. Then you would see something like this sigmoid pattern. In a forced regression, like what we saw in the previous, in the Lapout patterns, where we had that falling stage, we could, for example, see something like these oblique sets of reflectors here. Or then third, we have this complex type, where we have moundy features, hummocky features, or deformed features. Now, when I show you the case study from Penobscot, we're dealing with a mixed siliclastic carbonate system. We see both sort of siliclastic classic shapes, such as sigmoid, oblique, and so forth, but we also have these mounded shapes where we have reef buildup. Also, in general, like karsts in carbonates can be very chaotic, deformed. So these also can be quite helpful when trying to sort of differentiate your different packages using the SSIS tool. Another thing that's important to note here is that when we talk about these models, this table is from Katuneanu 2017, is that different authors use or have come up with different models. So these are some of the models that are offered in OpendTect in SSIS, and we can see that they talk about the same concepts, but they set their, for example, they set their sequence boundary a little differently in accordance to what their data at that time was suitable for. So for example, in the depositional sequence number 3, our sequence boundary is at the end of relative sea level fall. But in a genetic sequence, it would be at a maximum flooding surface at the end of a transgression. So it's important to note here that these different models, you don't have to try and fit your data to sit in a certain model. These are quite flexible in that sense. And that is why we offer a multitude of different models that are shipped with the sequence stratigraphic interpretation system. So, for example, we have here the depositional sequences 2 through 4. We also offer genetic sequences and a TR sequence, transregressive sequence. We could pick out channel stages just in generic stratal packages or sequences with arbitrary numbers, fluvial depositional sequence, and so forth. Now, we also offer sometimes your sequence boundaries, or where you want to place your boundary, is not clear or it's not uniform. You may want to include what we call a transition zone, where you will have a smooth transition from one package to the next. And then also you will see here where you define your top of your sequence boundary. So this goes kind of back to that slide we saw, the table where this sequence boundary was defined as different surfaces. This you can set here. Now, as of late, we have included also 2 new models, the AIGR and the BCFS models. This is work from Gardner and some others from 2008. I have that reference for you at the end of the presentation in my references. Now, these 2 models are more suited for kind of deep water type of settings, where the AIGR stands for Adjustment, Initiation, Growth and Retreat. And the AIGR model kind of starts with an adjustment phase, which defines the initial profile, gradient, and topography. The initiation, growth, and retreat phases then describe variations in sedimentary response. Now the BCFS model, the BCFS here stands for Build, Cut, Fill, Spill, and it's more correlated to confined or unconfined flows in channels, overbank, wedge, and lobe sedimentary bodies. As mentioned, we offer these different depositional sequences, 2 through 4. We can use a simple transgression-regression sequence, genetic sequence, channel stages, and then these two AIGR and BCFS that I mentioned. But what's also important to note here is that you can create your own. This is a flexible tool where you can go in and you can define your own packages. You could just pick packages starting at package 1 and go about it that way. Let's look at the workflow next. So I have a little chart here where we start with either 2D or 3D seismic data. We need to look at the data first, of course, and then do data conditioning as needed. We, in general, recommend that you start by creating a SteeringCube from your 2D or 3D seismic data. The SteeringCube is the dip and azimuth component of your seismic reflectors. We can then utilize that information in a dip-steered median filter type of attribute. We could also go ahead and do spectral bluing or sort of frequency boosting, frequency enhancement. Or we can utilize some of these later machine learning tools for denoising that are available. Then what we need to do is create again a SteeringCube. So if we have applied data conditioning, we may want to create a SteeringCube again, specific for this workflow, for detailed type of work, for horizon tracking. In general, many times I would recommend the fast Fourier transform algorithm for this type of SteeringCube. This is of course very data dependent. You need to look at the data. Are we dealing with layer cake, flat geology, or are we dealing with high dips and so forth? And then we need to adjust the step outs accordingly, according to the data. Once we have that SteeringCube, we can then go ahead and create the HorizonCube. As mentioned earlier, the HorizonCube, we will have a look at that here in the coming slides here. In general, I would say it is sort of a compromise between detail. If you want to work in a very local sort of little cube or 2D lines, you can extract lots of detail. When you start expanding this, you may actually lose a little bit of detail, but then you will be working on a much larger area. And this is again the sort of basis for further sequence stratigraphic interpretation work. Now, what is the HorizonCube? Now, the HorizonCube is the DGB proprietary global seismic interpretation plugin. It gives you a dense set of automatically interpreted horizons within at least 2 framework horizons. We also do need key faults if those are present in your data. And what we get here is first of all, phase-consistent horizons. Nowadays, we offer algorithms that allow for these to stick to peaks and troughs and zero crossings. But because we get a high density of these HorizonCube events, as we call them, it becomes much easier to see subtle little changes in depositional patterns, in thickness changes, and so forth. And the HorizonCube works, of course, both for 2D and 3D. Now, applications for HorizonCube, of course, today we'll focus on systems tracts and Wheeler diagrams and so forth. So traditionally you would have used a HorizonCube to do sequence stratigraphic interpretation, to flatten, to create Wheeler diagrams, or you would use it to maybe correlate well markers or correlate things between your wells. But we can also utilize HorizonCube to create better GeoModels. We could utilize it for seismic inversion, and we can utilize it to propagate properties from wells across the seismic volumes and create rock property prediction volumes. Some other applications would be, say, pre-drill geo-hazard identification. We could, for example, create a HorizonCube in the shallow section and then do straddle slicing in a 3D view, slice up and down using several different useful attributes to try and pinpoint where we might have geo-hazards. In unconventionals, we may use it to pinpoint sweet spots, or in well planning, we could utilize it to just find good spots for the well. So these would be some of the applications for HorizonCube. This is an example from McDonough and some others from 2013. It's a exploration project offshore East Africa, where we have these long regional 2D lines. Looking at the seismic alone is fine, but it's hard to pinpoint here features of interest. So in this case, the HorizonCube density attribute was used to reveal sort of where we have an inferred high rate of sedimentation versus a low rate of sedimentation. And what we got from that is, you can see here, these bluish colors show this backstepping fan system. Now, after we have the HorizonCube, we can then move on to the SSIS interpretation itself. The idea here is to, of course, increase the understanding of the depositional history and find stratigraphic traps. We can utilize both structural domain and we can utilize the Wheeler flattened domain. So I will actually explain this diagram once we do the demo here in a little bit. We can then actually take our picks, take our system structs that we have picked, and we can post them back into our structural domain so we can see our different packages in our structural domain and do further work that way. Next, let's talk a little bit about the case study that I have prepared for you from the Penobscot dataset before we move to OpendTect. So the dataset here comes from offshore eastern Canada. The Scotian Shelf, this little red arrow here points to this little point here. This is a screenshot from TerraNubis, by the way. You can go and download this dataset for yourself from TerraNubis.com. An excellent dataset with a mixed siliclastic carbonate setting. We're dealing here with the Abenaki carbonate bank formation, and it is sort of embedded in this Sable Delta clastics fans. Now here we are in OpendTect, and I already have a seismic line, a cross line in this case, with a HorizonCube overlay. So I have created here, this is just the structural domain with a few framework horizons. Another thing I'd like to do is create a flattened scene. We're not talking about the Wheeler scene just yet. The way to do that is to go into your object tree, right click the horizon you'd like to use as your datum. Under workflows, you then have create flattened scene. Now what that does is it takes your horizon and flattens along that, and we can have a look at how that looks like if I just tile my windows here. Like so. This is my flattened scene, and this on the right side, and on the left side you see my regular structural domain. So we've simply flattened along a datum here. The other thing that was mentioned in the presentation was how we want to use the Wheeler scene in combination with the structural domain to look for variations or shifts in the depositional patterns. The way to add a Wheeler scene would be from here in Scene, New Wheeler. Choose either 2D or 3D, depending on the HorizonCube type you're working with. And that will automatically generate a Wheeler scene. I have already gone ahead and created my Wheeler scene. You can see above here. Now, when I use the slider to move these arbitrary HorizonCube events up and down, it's synced across all these scenes. So I can use a section slider, and I can move it starting at the top. We can move it up and down. The idea here is, of course, now to make picks here where we see shifts in these depositional patterns. For that, we need to open the SSIS tool. That's done here from this SSIS icon. We pick 3D for 3D as we're working with 3D, and it should open up your Sequence Stratigraphic Interpretation System window. Now, I've already made some picks here, but we'd start from a blank interpretation when this is opened up the first time. So let's go ahead and blank this out like so. So this is the SSIS interpretation main window. We have our sliders here to the left, work the same way as the section slider that we saw just now. We have some other tools that we can utilize here. We can save and open, retrieve multiple interpretations. So once we have made some picks, we can save. We can retrieve them later. We can select our models here. We have some other settings here. Some other options here are we can view some statistics, and we also have a sea level curve option here to load something externally. Now let's go into the models. In this case, I want to use a simple TR sequence, so I will select that, and you can see that when I select this one, it is going to draw automatically the face, and it's going to call the surface like this. So for an RST, the surface is going to be SB for sequence boundary, and a maximum flooding surface is going to sit on top of a transgressive systems tract. And then we can also utilize undefined. We can also optionally here include transition zones if we want already here. Or we can add model. We can change anything in these fields. So we can call these things as we see fit. We can change the face as we see fit, and so forth. I will just be using this TR sequence for now. We'll change that. What we want to do now is start. I like to start at the base. So what is happening here is that we're seeing some shifts already here right at the base. We have this sort of, everything sort of building up here. I'd like to insert my first boundary. Let me turn off the seismic for this one. It becomes a little bit more clear. I'd like to insert my first boundary here where I see this little shift from left toward the right. So at the base of that, I will insert my first boundary. And you see it adds, when I click on insert here, it adds an unassigned boundary here. I can then right click anywhere in this column and select a systems tract. I'll leave this as undefined for now. We can keep moving. Where I see that the system shifts again back toward the left, I want to again insert a boundary. So we can go ahead and click insert again. And this way I would be moving upward. But you see, I have made several picks here within this first bounding horizon, and that may be what you want to do, but we also have included higher order interpretations as of late. What I could do is I could handle this sequence or this package as one. So I would insert a boundary here and go ahead and get rid of these. Insert a boundary here, and then right click here, assign it, say, a RST. But then I would like to make some more higher order picks here internally. What I can do is I can go ahead and insert, add second interpretation order, and it's going to add a second column here. Then when I make the pick, I just make sure that this is set to order 2. And when I now make a pick here, I can then choose something else for this one. We can use independently another model also for the second order. So let me go ahead and change I will just use straddle packages for this one. And I can then assign package 1. Then move up where I saw that thing move from left to right and back. And insert again. And I can assign this package 2. And then my third one would be on top of that, where it shifts back. Package 3. And so forth. So we can make sort of a main interpretation here on the left side here in this column, and a higher order interpretation on the right hand side here. Then if I want to go back to my sort of lower order interpretation, I would select this drop down list here, select order 1, and I can go back to begin sort of my main sequences. So this all looks like it's shifting here from left to right. So I will assign this also an RST. Then we get this big package here, shifts from right to left. Go ahead and insert a boundary here. Then shifts back toward right. I could call this a TST. And then I can make internal picks in here if I see some higher order information. And this is how we would go about making the picks. I can then bring back something that I already did here, where I've picked some packages in this way, almost all the way to the top, where we have a simple TR sequence picked for order 1 and just arbitrary package numbers for the order 2 picks. Now what I can do with this now, of course, is post this back into my structural domain. So I can go back here to my scene 1 and I could choose to add a system tract display. And in this case I want to view just the first order. And it will show me my systems tracts, how they look in the structural domain, where the green here is transgressive and orange is the regressive systems tracts. We also have the option here to save surfaces. So we can save all our boundaries here by clicking this here. And what that allows us to do is then bring back these boundaries into our project as regular OpenTect horizons. And I could then, for example, further analyze some of these boundaries by doing, say, spectral decomposition. If you're interested in spectral decomposition, last month webinar was on that topic, so I encourage you to check out that webinar recording as well. What I've done is I've taken one of these interesting looking horizons within this Abenaki sequence. I've added a color blended horizon, and I have, like this, extracted 3 frequencies and co-blended them on this horizon. We see a few interesting things here. We have, in this whitish color where all the frequencies are present, we have this carbonate reefs, and we also have this lobe shape here, and this is actually from the Sable Delta formation. So this is a siliclastic feature, whereas these would be the carbonates as it's been interpreted. So these are some of the things you could then do with your SSIS interpretation. Let's go back to the presentation for a recap. So here we are back in the presentation. Just a quick recap. So the workflow is that we first want to look at our 2D or 3D seismic data, do data conditioning as we see fit, and then from that conditioned data we then need a SteeringCube. Here it's good to keep in mind that this is an iterative process, so you may need a SteeringCube for your data conditioning. So you would create that first, do your data conditioning, and then create another SteeringCube that's specifically for this type of detailed work, type of HorizonCube type of work, picking horizons and so forth. We then create our HorizonCube that is at the base of the sequence stratigraphic interpretation system. Then we move into SSIS. And here it's important again to stress that you should use whatever fits your data and not try and force models onto the data, so to say. You can create your own models. You can modify the existing ones to sort of fit your needs. Start by looking out for the Lapout patterns. What sort of big picture things do you see? And then look for shifts in both Wheeler and structural domain. You can pick your boundaries. You can utilize the transition zones and higher order interpretation if applicable. So you can make picks within the pick, so to say. And you can utilize the transition zones if you're unsure where that boundary lies exactly. And then what we can do is we can extract sequence boundaries or package delimiters, for example using the SSIS tool, but also we have a 3D slider. If you'd like to view the horizons in 3D, you can use a 3D slider instead, and you can extract horizons that way to kind of pinpoint these kind of interesting features. I've just highlighted that reef structure that we saw in the demo just now, plus this lobate feature. Here are some of the references I've used today. Please feel free to check them out. And I would like to thank you all for your time. Thank you for watching, and let's open up for questions.